Now I am going to discuss the execution of non-vector interrupt here. So that's why I have depicted all the block diagram related to this discussion that you can see over here. This is a memory, this is a main memory, and I have also segregated the part of stack memory here by this black dotted line. This is a microprocessor, and I have also remarked some important part of the microprocessor like the stack pointer, program counter, instruction register, instruction decoder, timing and control unit, as you can see over here. Now just comes to here, then you will find one externally circuit is connected to the microprocessor, and this external circuit is called the buffer circuit. What it does, it provide a particular opcode to the microprocessor. And what is the function of this externally connected buffer circuit? We will see the function of the externally connected buffer circuit a bit later. So now my question is, as we are going to discuss the execution of non-vector interrupt, so what is the non-vector interrupt? So the non-vector interrupt, the interrupt which don't have any particular address in main memory, is called the non-vector interrupt. So as an example, I have also told you the non-vector interrupt is the INTR. Out of 5 hardware interrupt, INTR is a non-vector interrupt, and the 4 is a vector interrupt. So that's why, as you can see over here, I have drawn INTR only, as we are going to discuss the execution of non-vector interrupt. That's why I have taken only INTR. So now my question is, how does the microprocessor process or execute this non-vector interrupt into its machine? So as an example, so I would say that, so to enable, so first we need to enable the IIF of the microprocessor. So IIF, what does it mean? It means that internal interrupt flip-flop. So how does the microprocessor enable this flip-flop? So to enable this internal interrupt flip-flop, we need to write a EI instruction, enable interrupt, this instruction to the main program. So when microprocessor will encounter with this EI instruction, this instruction will help to enable the IIF, internal interrupt flip-flop, to the microprocessor that exists. This IIF exists into the microprocessor. When the IIF will enable, microprocessor can get any interrupt request from the outside by this interrupt hardware pin. So first and foremost thing, that we need to enable this IIF by writing this EI. So this is the first and foremost thing. So during the execution of main program, microprocessor also check simultaneously whether the INTR pin is high or low. When the INTR pin will high, so microprocessor immediately accept the interrupt request from outside to the microprocessor. Okay, or you may say microprocessor immediately grab the interrupt request. So when the microprocessor immediately accept the immediate request, it will accept the interrupt request. So at that moment, what will happen? So let me assume one thing. So during the execution of 3-byte instruction of the main program, microprocessor has got a high INTR. So microprocessor has got a high INTR when during the execution of 3-byte instruction. Now let's see. So when the INTR pin will high, microprocessor grab or accept that interrupt request, then the 4 things simultaneously will happen here. So what are the 4 things? First, the microprocessor will complete the current instruction that it is performing. Now it is performing the 3-byte instruction, as it is, this is a first address for the first byte, this is a second address for the second byte, this is a third address for the third byte. So it will first complete the current instruction and will hold this particular address. The program counter will hold this particular address complete the instruction and stop the all execution of main program. Stop all the execution of main program. This is a main program execution, so it will stop there. This is the first thing will happen. Second thing, the microprocessor will disable the IIF. Now IIF is disabled. IIF, internal interrupt flip-flop, will disable. That microprocessor will not allow any kind of interrupt request at that time being. That's why it will disable the IIF. This is the second thing. Third thing, microprocessor will send an active low signal to this buffer circuit that you can see over here. Microprocessor will send an active low signals to this buffer circuit by this INTR pin, interrupt acknowledgement pin. We have seen in our interrupt control block there were 6 hardware pin, 5 were the interrupt hardware pin, and 1 was the INTA pin, interrupt acknowledgement pin. So by that acknowledgement pin, microprocessor send a signals to the above output externally connected buffer circuit. This is the third thing. And fourth thing, this INTR microprocessor also send a message to the externally connected input output device by this INTR pin. What it will send a message that the microprocessor will not able to take or will not accept any kind of interrupt request at that time being. So this fourth thing will happen consecutively when microprocessor will accept any kind of interrupt request from the outside through this hardware interrupt pin. So now what will happen? Now microprocessor will save the next instruction address. So these were the 3-byte instruction. What will be the next instruction address? Next instruction address will be 8007. So microprocessor will store or will save this next instruction address to the stack memory location. So as you can see, so this is a 8007. Then how does the microprocessor store this particular address to the stack memory location? As we have seen in our early lecture that this is a higher byte of the address and this is a lower byte of the address. Higher byte of the address will go to the high address value or high address location, which is 9005. As we are performing a write operations to the stack memory location, so the stack pointer will point the higher address and will decrement its address by 1. So here you can see it decrement by address by 1 and the write operation will start to perform. So higher byte of the address will go to the higher address location, lower address byte will go to the lower address location. That you can see 07 is 9004. So in that way it will store the program counter address value, or you may say the next address value or next instructions address into the stack memory location. It's basically a bookmark. So when microprocessor will complete all the execution related to the interrupt request, it will start to perform the execute the main program from this address. So that's why it is storing this particular address here, that it can retrieve that address later and start to perform the rest of the main program. So these were the things. So now what will happen? Now just comes to here, this externally connected buffer circuit that you can see over here. So this externally connected buffer circuit will provide a particular opcode to the microprocessor. It basically provide or it basically place this particular opcode to this data bus. As you can see, 87 to 80. So this data bus, then the data bus will place this particular opcode to the instruction register EF here, instruction register, and then instruction register will send that particular opcode to EF here. Then where it will send this particular opcode to the instruction decoder. This opcode will be decoded into the instruction decoder and the decoding message will come to the timing and control unit. When the decoding message will come to the timing and control unit, the timing and control unit of the microprocessor will come to know, or microprocessor will come to know that which operation it needs to perform. As you can see over here, this is a opcode EF, and by this opcode, after decoding that opcode, microprocessor will come to know that it is a software interrupt. That means it is a software interrupt which is a RST5. So this software interrupt has its own address location in main memory. That you can see here that I have defined, or I have written here the specific address location, as well as I have also written the next software interrupt, which is RST6. It has a particular opcode also, and it has a specified address location also. I have defined the address location also here for the RST6. Why I have done that you can understand the difference between these two specified address location, which is a 8-bit that I have told you. This is a 8-bit address location. The difference between these two address location is 8-bit. Now the microprocessor, now the timing and control unit of the microprocessor will instruct to the microprocessor that fill this program, erase this value, erase this next instruction value, and fill this value, fill this program counter value with a specified address location 002, specified address location with the particular software interrupt, which is RST5. So now let me repeat again. So timing and control unit of the microprocessor will instruct to the microprocessor fill this program counter with this particular, with a specified address location that you can see over here 0028, and for this particular software interrupt, which is restart 5. So now what will happen? Now the program counter will start to increment this its address by +1 as usual as it does. So it will start to increment its address one by one, and according to that way, microprocessor will also execute those subroutine which have been written, which have been already written to this specified 8-bit memory location. As you can see, this is a 8-bit memory location. So this all 8-bit location are the full of subroutine that you can see over here. So you can remember that I have told you, so for the execution of non-vector interrupt, we microprocessor do not know the address of the subroutine. That's why we always supply the address of the subroutine by connecting a externally input-output circuit, buffer circuit with the microprocessor that you can see over here. So I have discussed this point when we are talking about the non-vector interrupt. For the vector interrupt, microprocessor already know the address of the subroutine. That's why if you will draw the block diagram for the execution of vector interrupt, at that case we will not use, or we will not draw this external part. We will only use the microprocessor and the main memory. But here, as we need to supply the address of the subroutine, that's why, as you can see, this is the opcode. By decoding that opcode, microprocessor will come to know the address of the subroutine that you can see over here. So this was a process. So by executing those subroutine, when microprocessor come at the last of the program, as you can see here, it will face two instruction here. One is a EI, another is a RET. So EI, it will first face EI, that you can see enable interrupt. That means this instruction will again enable the IIF, internal interrupt flip-flop. That means which helps to microprocessor get the further interrupt request. Okay, and then it will again face the RET instruction, which means that return instruction. This instruction RET helps to return from the subroutine, execution of the subroutine, and come back to the main program. So when microprocessor will come back to the main program, microprocessor will straight go to here and will retrieve or read the value of the main program, which was stored here as a bookmark, that you can see, which was stored as a bookmark here during the execution of program. Then it will retrieve or read the value from here and store that value into the program counter. Then the program counter will start to process or start to execute the program which was remained to be executed. That means from this part the program was interrupted, so the program counter will start to execute the process from rest of the program which was remained to be executed. So that is a process of execution of non-vector interrupt. The difference between vector and non-vector interrupt is, this vector, for this non-vector interrupt, we supply this address of the subroutine by connecting this hardware or connecting this buffer circuit externally. But for vector interrupt, we will not connect any kind of vector circuit, we will not connect any kind of buffer circuit externally, because microprocessor already know the address of the subroutines. So let me compare. So now let me just revise the process briefly that we have done here. So now let me define whole process in a brief way. Then I would say, so first we need to active the IIF. IIF is here, internal interrupt flip-flop. So when this IIF will be active, how does it will be activated? It will be activated by write a EI instruction. When this IIF or internal interrupt flip-flop will be activated, then microprocessor can get any request, any interrupt request from the outside. When any interrupt request enter to the microprocessor, microprocessor will immediately stop the execution of its main program and store the next instruction address into the stack memory that you can see over here, 800, where the next instruction address of, as it has stored here as a bookmark. Then the microprocessor will start to process immediately the interrupt request. It will, how does microprocessor will process those interrupt requests? Microprocessor will process those interrupt requests by executing all those subroutine which already has been written into a specific address location. When all the subroutine will be executed, microprocessor will complete the execution of interrupt request. Then microprocessor will come back to the main program which it has been performing for a long time. Then microprocessor will come straight to here, will retrieve that particular main program address, store this address to the program counter, and will start to perform the rest of the main program which was remained to be executed. That means first interrupt, when interrupt request will be come to the microprocessor immediately perform the interrupt request, then it will perform the main program. So that the way this was the execution of non-vector interrupt that I have elaborated here.